So today's final plenary speaker is from session 4, Dr. Dimitri Gutierrez. Dr. Gutierrez is the director of the research in oceanography and climate change at the Peruvian Marine Research Institute. As a biological oceanographer, his research is focused on basic responses to natural and human-induced hypoxia, effects of climate variability on productivity and subsurface deoxygenation in the coastal marine systems in the southeastern Pacific. Today, Dr. Dimitri Gutierrez will talk about the climate variability and ocean deoxygenation over continental margins associated to the Peru, Chile, and other upstream systems, and insights from proxy records. So welcome, Dr. Gutierrez. Yeah. Thank
you. Good morning. First of all, I want to say thank you to the organizers for inviting me and provide me this opportunity to share with you an overview of some aspects related with past deoxygenation or past oxygenation according to proxy records, especially in the tropical southeastern Pacific. First of all, we should talk a little bit about the oxygenation. Is one of the main concerns driven by the climate change. We all know that oxygen is a fundamental property for biodiversity and global biogeochemical cycles. And oxygen loss it represents a threat and a hazard for the sustainability of communities, ecosystems, and resources. Well, actually, the oxygenation has two aspects. We can talk about open ocean deoxygenation and also coastal ocean deoxygenation. For the open ocean deoxygenation, there are many studies in the last decades trying to project what would be the trajectory of oxygen loss given the greenhouse emissions and global warming. There is a consensus among the models that the global ocean would lose about 5% of the oxygen content because of this climate change effect. And there are at least 2 or 3 factors that contribute to the deoxygenation. One of it is solubility, decrease of solubility due to global warming. The other one is lower ventilation or changes in circulation, and higher oxygen consumption, and higher because of higher respiration. Actually, in the session 4, there will be several talks about models, about mechanisms, with people that has more authority than me in explaining these issues. The other aspect of global deoxygenation is related with coastal eutrophication. As you may know, there have been increasing number of reports of the so-called dead zone or coastal dead zones, which are just the hypoxic areas. And the number of reports has doubled in the last 20 or 30 years. It seems that this coastal deoxygenation is driven by nutrient input to the coastal ocean, which is in turn related with the increase of the human population and increase of industries and increase of all type of activities in the coastal areas. But I will not talk about that. I will talk about the open ocean deoxygenation And I will start saying that the current models, despite having a consensus about the global trajectory of oxygen loss, still have limitations to reproduce the regional distribution of oxygen changes. For example, on the left side, you can compare the observed oxygen trends in the black line and the model trends in the color lines. And it is easy to see that the models are not able to reproduce the tropical deoxygenation near the equator. And for the future, the models are predicting deoxygenation in the high latitude areas, but there is a lot of uncertainty in the tropical region. And if we compare the difference of oxygen comparing the RCP 8.5 scenario for the late 21st century versus the late 20th centuries, if we compare this with the internal variability of the models, we can arrive that the degree of uncertainty is even higher. There are very large areas in the global ocean where there is a very important uncertainty on what would happen. The hatchet areas in the lower panel on the right depicts these regions where the models are not able to reach a consensus on what is going to happen with global warming. Okay, so several of these regions where the uncertainty is higher actually are the current oxygen minimum zones in the global ocean. The 3 or 4 more important of these also intersect the continental margins. That is the case of the Eastern Pacific oxygen minimum zones, the tropical Southeastern Pacific, the Eastern Tropical North Pacific, and Eastern Subtropical North Pacific, and also the Arabian Sea. Of all of these, the Eastern Tropical North Pacific is the one which is more developed. It is the upper limit is very shallow, and the thickness is very large, reaching 1,000 meters of water depth. So, what are the tools to reconstruct the changes in paleoxygenation? There are a number of proxies. For example, the redox-sensitive metals, these metals precipitate under anoxic conditions in the sediment-water interface, and then they get immobilized in the sedimentary column. So when we retrieve a sediment core, we can reconstruct the changes of these benthic oxygenation conditions. Another proxy, which is very well used for the pelagic deoxygenation, is the delta N15 of the organic matter. This is because when there is oxygen deficiency in the water column, the microbial denitrifiers enrich the residual nitrate with a heavy isotope. Then this heavy nitrate is assimilated by the phytoplankton, and when the phytodetritus settles to the bottom, it conserves the heavy isotopic signature. So changes in the intensity of the OMC could be tracked by looking at the changes in the delta N15 of the sedimentary organic matter. Other proxies which are very used are the lamination presence in the sediment cores or the assemblages of benthic foraminifera. So let's take first an overview of what happened during the deglaciation since the last glacial maximum. As you may know, the warming pattern of the northern hemisphere and southern hemisphere differed a little bit. In the case of the southern hemisphere, during the period called Heinrich Stadial I, which was between 19K8 to 14K8 or 15K8 before present, the temperature in the Antarctica increased steeply. But in the northern hemisphere, the warming was much more rapid and much more constrained just after the Heinrich Stadial I. On the left, you may see the average records of pelagic denitrification, taken as a measure of water column deoxygenation, that was modeled and assembled by Jacquard in 2015. And there you can see, that is the top panel on the left, that the Eastern Tropical South Pacific records exhibit a behavior very according with the tuning of the warming in the Southern Hemisphere. That is not exactly the case for the Eastern Tropical North Pacific, but in the case of the Arabian Sea, which is the red line, the increase of denitrification occurred after this early deglaciation period and was more important during the Holocene. Second difference here is that while the Pacific records show a trend towards less denitrification from the early Holocene to the mid-Holocene, the behavior of the Arabian Sea records is just the opposite. I will come back about this later on. So now let's talk about the OMZ, the Southeastern Tropical Pacific, which is the region where we have done most of our research. The circulation system is very complex here because there are several equatorial currents impinging the extreme eastern southern Pacific, which are the equatorial undercurrent and the secondary subsurface currents, which are two actually. And the core of these undercurrents is about 100 to 200 or 300 meters of water depth. So these currents transport relatively oxygen-poor waters, but when they get to the coast of South America, they feed or contribute to the Peru-Chile undercurrent, which flows poleward from Peru to Chile. But as long as this transport is going on, the water is even more depleted in oxygen because of the accumulated respiration through the path. On the other side, from the south and much deeper, below 500 meters of water depth, we have the Chile-Peru deep countercurrent, which transports Antarctic intermediate waters, which are oxygen-rich waters. So, in general terms, we would say that the equatorial undercurrents play a role in the ventilation of the OMZ, especially in the lower latitudes, while these deep currents, which transport the Antarctic intermediate waters, plays a role in the ventilation in the southern part of the OMZ. The records of the glacial changes in oxygen are many. I'm just using one by Salvatecci 2016, where I want to orient attention to the behavior of the delta N15, which is in the blue symbols, versus the redox-sensitive metals, which are in the red symbols. As you may see, the increase of delta N15, the magnitude of increase of delta N15 was very strong during the early deglaciation, and then it showed a tendency to decrease towards the mid-Holocene. But in the case of the redox-sensitive metals, we observe in general terms a positive trend, with a lot of variability, yes, but a positive trend. This pattern of that the denitrification leads the change in the paleoproductivity has also been observed in other systems like Chile and California, I think. Well, what about the records, the proxy records in Chile? All of the records that are published show the same strong Southern Hemisphere signature. The jump of the delta N15 values is very strong during the Heinrich Stadial 1, which is on the left side. And it seems that here, the shifts in the position of the southern westerly winds play a very important role in terms of redistributing the primary productivity and also in changing the ventilation of the OMZ in this region. So it is, there is a consensus that during the last glacial maximum, the westerly winds were at a northern position than today, and the shift from lower latitudes to higher latitudes on one side redistributed the productivity, and on the other side changed the subduction of oxygen-rich waters from the south of Chile to the whole system. And that change may have had a contribution, a local contribution, to the signature of the oxygenation in this time period. Well, I will just comment very rapidly for the case of the California current. The signature of the delta N15 changes resembled both the northern hemisphere as the southern hemisphere, that is on the left side. But here as well, the global averages of benthic oxygenation shows that during the mid-Holocene, the oxygenation was lower than during it was more oxygenated during the middle Holocene than during the early Holocene. So the same pattern of better oxygenation in the middle Holocene that we see in the Eastern Tropical South Pacific could also be observed in the Eastern Tropical North Pacific. And the Arabian Sea exhibits a very different behavior because the factors that play are also different. Here, the dynamics of the system is governed by the monsoon variability. So the southwestern monsoon, which occurs during summer, promotes the upwelling in the East Arabian Sea and a lot of productivity, and this in turn contributes to the oxygen consumption and contributes to the oxygen deficiency in the system. So when we compare the differences between interglacials versus glacials, or during interstadials versus stadials, we always can infer the same pattern. That is that during warm periods, millennial warmer periods, for example, there is a stronger southwestern monsoon, and then the OMZ is amplified, and the reversal when we have global cold periods like the glacials or stadials. It is important here to say that the intensity of the monsoon winds are also related with the position of the intertropical convergence zone. So during interglacials or interstitials, for example, the ITCZ is shifted towards the north, and that is also associated with the enhancement of the southwestern monsoon. So what happened during the mid-Holocene? This period is considered a La Niña-like period for the Eastern Pacific. The reconstructions of the sea surface temperature across the equatorial Pacific indicate that the gradient was stronger during these 2 or 3 millennia in comparison with the early Holocene or in comparison with the late Holocene. And a number of proxy records are related with metals, geochemicals, biogenics, and also biogeographic changes in the South American coast confirm that this was a colder period with a stronger upwelling. It is believed that the undercurrent, the Peru-Chile undercurrent, was very strong during these periods, and that is strong that, for example, that the net sedimentation rate in the sediments was lower because increased erosion. What is interesting is that during this period, where the ITCZ was moved to the north, also in the Indian Ocean and in the Arabian Sea, the southwestern monsoon was stronger. But in the case of the southeastern Pacific, this period was or exhibited more oxygenated conditions than in the early Holocene. So what is the explanation for this? There have been several new research publications on this issue. And one possibility is that the enhancement of the water circulation also contributed to an enhancement of the undercurrents. And the undercurrents, the eastward undercurrents, in turn, ventilated the system and made it more oxygenated than before. For the last millennium, in the eastern tropical South Pacific, we have experienced global climate periods characterized as cold periods or warm periods. For example, the Little Ice Age from the 1500 to the 1800s was considered as a global cold period. And the medieval climatic anomaly, at least in the later part, is considered as a warm period in terms of the global air temperature. But the behavior of the productivity and oxygenation in the eastern tropical South Pacific was very clearly tuned with these global climatic changes. During the Little Ice Age, for example, the paleoxygenation proxies indicate that the oxygenation was weaker and the productivity was also weaker, while the opposite occurred during the MCA. The explanation here is that during the LIA, the water circulation was weaker, the ITCZ shifted to the south, so the wind forcing was lower and the system was more ventilated. This mechanism could also explain the changes for the MCA and the changes for the current warm period, where we find, in general terms, at this time scale, kind of La Niña-like conditions. The records in Chile going to the south show a great level of coherence to what we have observed in Peru, but until the Little Ice Age. For the last 100, 200 years, there are some differences. But most important than that is that in the southern areas along the Chilean coast, there is a decrease of the nitrification and a decrease of productivity, which is not observed or is not clearly observed farther north. So this is possibly a signal that a process in this region is ventilating the OMC along the Chilean coasts. Well, I will skip this. And just to finish, now if we focus on the last 100 years, the Anthropocene records of oxygenation in the Eastern Pacific, we can compare the trajectories of the denitrification in Peru, which is the mid panel, in Chile, which is the lower panel, and in the Californian coasts, by this work by Deutsch et al. 2014, we observed that there is a coherence in terms of a decrease of the nitrification, and that would indicate an oxygenation trend during this time period. With just a disclaimer, because in the Deutsch records, there is a reversal of these trends for the last 20 years, which are not observing in the case of the Peru and Chilean records. So, just to finalize, I think that the sedimentary records evidence the influence of climate variability on the expansion, contraction of the OMCs. Actually, paleoclimate models are very valuable tools to investigate the multiple processes and factors involved in the natural climate-driven oxygen changes. We have observed that the factors that are in play in each of the systems differ. They are not common mechanisms in each case, and that adds complexity in terms to understand the mechanisms that are behind the observed trends and probably our ability to predict the future. Thank you very much.
Thank you, Dimitri. We have a time for 1 or 2 questions. Please come to the microphone, please. So I would like to ask about the relationship between the anchovy and sardine fluctuation. So you may have information of the fish scale from the core. Is there any relationship with activity?
Yes. Modern observations indicate that habitat compression, because of the very shallow oxycline in the Peruvian system, enables the anchovy to thrive in the coastal region with very little interaction with predators and possibly excluding sardine out of these areas. But when we look at the past records, at least at multi-decadal to centennial or millennial time scales, what we observe is a high degree of synchronicity between the changes in the populations of the 2 species. So it seems that because this is a bottom-up system, the carrying capacities of these species are more important than any ecological interaction they could develop.
Other questions? Okay, so thank you again for Dimitri. Thank you.